Here we have the recap of our 3D Maxwell exercise. We're going to focus on Faraday's equation, which is the curl of E is equal to minus mu time derivative of H. Now what we did in class was we showed that we could write a plane wave solution to the wave equation in this form. E, the vector E, is equal to a constant vector E0 times e to the j phi. And I use phi because otherwise if I have to write it out all the time, it will get very messy. Phi is equal to omega t minus kxx minus kyy minus kzz. At fixed t, when phi is a constant, this defines, as we saw, the equation of a plane. Now, in order to take the curl over here, we have to do things like taking the x derivative of ey. And for example, the z component, we're going to do ddx ey minus ddy ex, which is exactly this term here. What we need to do is to write each of the components here. Well, I have the components written. They're just the component values of E0 multiplied by e to the j phi. So you see them here. The exercise really is to compute these curls. So in the next slide board, I will show how to compute this very straightforwardly. And then we'll see something quite amazing in terms of getting a relationship between the k vector, which has components kx, ky, and kz, and the frequency and mu and some other constants. So we'll see how that all fits in the next board. Let's continue our calculation. The z component of the curl of E is the x derivative of ey minus the y derivative of ex. Z component, it's this times that, which is dey dx minus ddy of ex. Now we write the components as we discussed earlier. Here's the x component, here's the y component, and we're going to have to take the derivative dey dx and dex dy. Well, the amplitude vector with components e0x, e0y, and e0z is a constant. So if I differentiate with respect to x, constant times exponential, derivative of exponential, derivative, chain rule here. Derivative of exponential is the derivative of the exponent, then multiplied by e itself. So phi is this quantity here, and the x derivative of that is minus kx. And there's a j because of the j from here. So we have minus jkx e to the j phi. Similarly, the y derivative given here. Now we substitute into our expressions that come into the z component of the curl. And we now have to assemble this and substitute in our derivatives. So we'll do that in the next slide. Here's the z component again. We're going to assemble everything. Partial derivative of ey with respect to z minus partial derivative of ex with respect to y. Let's substitute in. Recall that the derivative is just the exponential derivative with the chain rule. So if I take dey dx, I have the constant e0y, the x derivative of e to the j phi, which we saw in the last slide was minus jkx e to the j phi. Then we take minus d dy of ex, and we get that. And of course, we can factor out e to the j phi, and this is what we get. Now we have to do it for all the components, assemble, and then see if we can find a pattern here. Let's continue finishing up this calculation. Here we see the determinant that represents the curl. And in the previous slides, we showed that differentiating with respect to x, y, or z brings down a minus jkx, minus jky, or minus jkz as a result of differentiating the phase. The phase of the wave is omega t minus kxx, kyy, kzz, and we saw in class that this can be written as a dot product. So for a fixed time, if phi is a constant, that means you're sitting on a peak or a zero crossing or a trough point on the wave. This is a constant, which means we have a plane. So on the collection of points that define a plane, phi is constant. So now we have a picture. Let's finish the calculation, just grind it out. On the left-hand side of Faraday's law, this is the first step for doing the curl of E when E is given as in the previous slides. Now, let's substitute in for the x, y, and z components. And of course, they're just an amplitude in that direction and a phase. And there's the phase. Same for y, same for z, directly substituting in here. Now you can see that this is just the cross product of the components of k multiplying or crossing the components of E, and E components are this times e to the j phi and so on. So we can in short form write this relationship. Now let's look at the right-hand side of Faraday's law. We haven't given much sway to that, but here it is. H0 is a constant vector as before. And when we differentiate e to the j phi, an omega pops down, a j pops down, e to the j phi is j omega times, this is a constant amplitude, and the exponential, that stays as is. And now we have this for the right-hand side, so here it is here. So here's our almost final result. Now we just have to do one thing, and that is cancel the e to the j phi's. And now you can see we have the following relationship, that k cross E naught is equal to, the minus signs cancel, the j's are done, so that's going to be omega mu omega h naught. Now, we're going to interpret this in a minute and close the loop, talk a bit about dot products. So this is just what we got in the previous blackboard, lightboard worth. K cross E naught equals mu omega H naught. So let's look a little bit at interpreting all this. First of all, we know that the magnitude of K is omega over C. Where c is the speed, 1 over the square root of mu epsilon, so the magnitude of k is that. That's the magnitude. It also is a vector, so it has a direction. The direction is normal to the plane of constant phase. So now we just substitute this in for k. There it is. Cross E naught is equal to mu omega H naught. Nice things happen. Omegas cancel out. This is square root of mu here, and that's mu here. So one of the square roots goes out. So this will become, when we cancel out the square root here, we'll lose square root here, and we'll be left with the square root of mu there, and divide by epsilon. So we'll get this. So we can see that H naught is perpendicular to N and also perpendicular to E. Well, we know that E is going to be vibrating in this plane. So that means that N, E naught, and H naught are mutually perpendicular, and that can be verified, as we'll see in recap conclusion 2, by doing the same calculation with Gauss's law. In other words, in the next screen, we're going to finish this off completely by showing that E naught is also perpendicular to K. The other thing is, look at this. This should be familiar. It has to have the units of what? Well, let's do the units. Volts per meter. H, amps per meter. Volts equals what times amps? This has to be ohms. This is called, again, the intrinsic impedance. The material impedance, if you like. So now let's just finish this off completely by looking at recap conclusion 2, where we'll show that E0 is perpendicular to K. Here we are now with the final piece of the conclusion, and that is this. We're going to show in the second portion of this light board that K and E are perpendicular. The top two equations, this is what we had before from Faraday's law, that N, E0, and H0 are perpendicular in the sense that H0 is perpendicular to N and E0. N hat is the direction of K. So let's look at Gauss's law, del dot E equals 0. There it is written out. Substitute in for EX, EY, and EZ and differentiate as before. We get this. Minus JKX, E0X, e to the J phi, and the same for the other components. We can factor out minus J e to the J phi, and we've got this, Kx E0x plus Ky E0y plus Kz E0z. This whole expression must be equal to 0. This is never 0, so we can cancel it out, and you can see that this has the pattern of the dot product. K dot E0 is 0. That means that K vector is perpendicular to E0, or equivalently N hat is perpendicular to E0. And now we've closed the loop. That we see now that N hat, E0, and H0 form a perpendicular coordinate system with N hat normal to the wave front as the wave moves through the material.